Yeah, thanks for having me, and I would have loved to be there, but things don't. Things are complicated. Yeah, so I would try to give you, since your the conference is mostly about transport and things like that. I would like to give you an idea about some of the things we're gonna some new ideas that we think we're gonna follow up in the next few years, which is something like we did all these experiments on one-dimensional systems, and I think we can build really cool quantum machines out of those, where you basically use the quantum field theory description of that low-dimensional system as your medium on which to build the machines. And the basic ideas are now about 3 years old in this book on quantum thermodynamics, and we had a long paper just in PRX Quantum, which describes some of these details. I want to show you a few of those things. Of course, the experiments are just starting, and I can't show you, heat flow or anomalous flow or things like that yet, but we can show you, I think we have all the ingredients in there to really do this stuff. So what's the basic idea? Is we want to build machines and study processes where first of all, the number of particles is large, and quantum mechanics is essentially to describe the dynamics. Yeah, and for that, so we want a quantum many-body system that's described by quantum field theories. And why we think is it interesting? You might give you an interface between statistical mechanics and quantum physics, and you can probe the role of information in a quantum thermodynamic process. And when you probe the role of information, we can say that basically what the machine can do is what I know about it. And also we basically want to build quantum machines that I cannot really calculate in a simple way, but in a classical computer. And as you will see, if we use a very strongly correlated quantum Stein-Gordon field on the fluid of the machine, we basically have something that is in the non-equilibrium sense, way beyond anything you can calculate on a classical computer. So these effective quantum field theories are very powerful tools to describe many-body quantum systems. And you can view it in a way of the things that I want to tell you afterwards, that it's a quantum many-body system from which this effective quantum field theory emerges. At temperature T equals 0, you can basically say this is the vacuum, and the excitations being the particles, the energy density being the geometry, and all these other things you can think about, and you can realize them in the lab. And examples, of course, is the 1D superfluid and the latential liquid, which we heard before as an example of something that looks like a relativistic quantum field theory. If you take two tunnel coupled superfluids, you get this Stein-Gordon model, which you can map off onto many different problems, ranging from the old theory problem to string breaking in QCD and things like that. And they're right. And here I want to use this quantum field theory to implement these thermal machines and to study the role of information on quantum thermodynamics. So I basically this would be the outline of what I want to talk in more details. So what's the basic idea of this quantum field machine is basically you take a many-body system, which is described by quantum field theory, and you can divide it into reservoirs, pistons, and another reservoir, and you can manipulate the reservoir, the piston, and in such a way that you can maybe, you couple the reservoir 1 onto the piston, you can compress the piston, you connect the piston to the reservoir 2, and therefore you can pump energy from one reservoir to the other. This would be a simple machine that you can think of building. And this reservoir could either be a very simple latential liquid, then the theory is simple and we can write it down, or this could be an extremely strongly correlated, Stein-Gordon quantum field, where I don't have any chance that I can do the calculations, because it's basically all orders of correlation functions. All order connected correlators are the same order and about 1. In every order, you get new information to the system. So what I think what is cute and why I thought that this is an extremely interesting part in there, if I build something like that, I have lots of information about the reservoirs, and I could think about, you can look at this, you can build the machine to being extremely non-Markovian. Remember, we did this experiment a few years ago where we showed that if you design your dispersion relation correctly in a quantum fluid, you can get recurrences of tens of thousands of particles. You get quantum recurrences of coherence, tens of thousands of particles. You can think of, you design your reservoir in such a way that, there are certain times when you recouple them, when it has basically all information that's there in the beginning, and in between, it's in a Gibbs state, and it looks like a completely classical reservoir. Yeah. Depending on how strong we make the coupling, we can either make strong coupling or weak coupling. There's another question which is extremely interesting in there. I think in our systems that we have, splitting and coupling creates additional noise, which is usually completely neglected in machines. But that splitting noise is basically the beam splitter noise, and which was the noise that we measured in the pre-thermodynamical experiments some years ago. So these are basically things that every connection, every other things that you do gives you an additional quantum noise, which if you go to the thermodynamic limit, basically has no influence, but in a finite machine can be a defining problem. And the other thing is that, we have shown that, depending on how we do the coupling and decoupling, we can create entanglement between the different parts. If you have entanglement, you can think of using that entanglement as a resource to make, for example, heat flow in the wrong direction. And as I said, we can make this machine can be made out of a strongly correlated St-Gordon field, which you basically have then a machine that's built out of a strongly correlated quantum fluid. And you can also think about doing many of these machines in parallel. And if you do the machines in parallel and you operate them in parallel, then you can think of that all classical physics things would be equal and they would drop out in the differences. But everything that has to do with the quantum properties and the quantum noise will be different. And they'll give us a direct handle on showing what are the quantum properties of this type of machines. So this is basically one of the motivations why we thought that it might be interesting to really look into that, building quantum machines with these quantum fields. So what's the idea behind there? When, as I said, which quantum fields we think of, we usually do most of our experiments with bosonic latential liquids, where we have a very strong confinement in transverse direction, but be so cold that you describe a field which has a phase, thermally, has a phase and then density fluctuations with a populated high excitation, and you can solve that with it's an example of the linear model or the latential liquid. And if you take two, you get this St-Gordon model which has this non-trivial cosine term in there, and which from where all these topological excitations and the strong correlations come into the model. And we can implement it very easily on our chips, where we can reach this question, or we can reach temperatures that are very small and temperatures that are much smaller than any interaction energy. So, and we have all these tools available, which are basically, we can detect every single atom in the trap with unit detection efficiency, basically, and we can measure, phases and order parameters and all the way on that. Okay, it's just to recapitalize what you can do. I mean, you can look at the relaxation of such a system, which goes to a light cone to a generalized Gibbs ensemble. And in this Gibbs ensemble, you see already that everything that's below here are interesting quantum states of many body modes you produce. And you can have some further decay, and you can see that, if you do it right, you see coherences where your recurrences, where all the quantum coherence comes back. The other thing is that you can make this St-Gordon model, which is basically by adding a tunnel coupling. Then if you add a tunnel coupling, you basically get, following this Kritzer-Pokornikov seminar, you get this additional harmonic term on it. And so you have a potential for the St-Gordon field with the cosine. An interesting thing is that you can basically, we can dial this in an experiment. We can dial the strength of this cosine term, we can dial in the experiment. And characteristic for that is that it's a very strong, that can be a correlated quantum liquid is basically because you can measure these connected correlators, which basically tells you that you can measure these things, and you can really verify that the connected correlators that you measure are exactly the ones that you would predict in equilibrium, and you can see topological excitations. We can also see this directly, and we can basically we are limited in our analysis of correlations, not by the experimental data, but just by the computational complexity of doing that. And so it's something that is, tells you how complex of a structure you can do. What might be also interesting to note is that, we have by now the methods to extract out of these correlators, propagators, and vertices, and you see things that you usually remember only from cosmology and high-energy physics. You see running coupling constants, running effective masses, and everything that have to do with the quantum corrections that come about due to the strong correlations in the model, and we can directly measure them now. Yes, we can look at so. And what is also interesting is there are some tools where we can, to really measure the quantum states. You basically want to do some kind of tomography. And so you want to know both quadrature components of your excitations, and you can do that by quenching into a free model and watching the Wigner function rotate, and you can basically reconstruct that, and you see this is the data, and these are a reconstruction. And depending on where you do your reconstructions, even if you do a reconstruction right there in the middle, you basically see you can reconstruct that there's these recurrences in the system. So we have now lots of tools, I think, where we can really probe this type of experiment extremely nice. So the idea is now to really build this type of machines. And so we thought about, looking at the different primitives. What happens if I connect two of those things together? You have heat flow, and if you connect them together and take just a lattice liquid, you see a front of heat flow running through your system, and you can go and see, if you compress or if you decompress, you can see the system heating up. And if you can make a circle, you can see that in principle you can cool your system a little bit from compared to its original temperature. So in principle, you can work this type of machines. Now the question is, how can you implement them? And for that, we have to be able to, arbitrarily control the external position, the external direction of your one-dimensional quantum fluid. And you can do that by, projecting light fields onto that. And you see, you can make it a very long box. You can make, barriers. You can imprint a single excitation on there. And by the way, if you do that, you can print the excitations on there and look at them damping. And it's beautifully described by our extension of, the standard GHD doesn't explain it because the damping isn't really in there. But if you take this extended GHD, which we published beginning of this year, it describe all these damping of these excitations in a very beautiful way, which is just writing things up right now. And then we can compress and make it hotter, but we have to go and do some, learn how to do this in optimum control. And because otherwise, if you don't do it optimum control, you get a focusing of you create excitations from compressing, get a focusing on that. And we can go and measure local temperatures by looking at the two-dimensional, at the 2D two-point correlator, where basically if you take it at a point and look at the outside, you can see this on a log scale, the decay of the correlation function. And if you have a barrier somewhere in between, you see that this barrier basically breaks the correlation. If you decouple, the correlations are completely broken. You see that it goes down by 5 e-folds. The correlation function goes down by 5 e-folds over very small things. What we're learning right now is how we can measure local temperature. How small of an area can I assume that it has a temperature, and then we learn how to, we can compress one part, couple them, put them together, and look at heat flow. This would be, so to speak, the first experiment, which is In fact, we're trying right now. It's not done yet, but it looks like that at least we see some of the things of really heat flow going to this, from one system into the other, which will be the first step. So, so basically what you want to verify first all these operational primitives of this quantum field machine, like compression, decompression, moving, splitting, decoupling. And what we basically develop methods for these local measurements. And then what you really, want to start, this first thing is start heat flow, connect to examples with different temperatures and look at the heat flow and see where it comes from, see what normal covariancy does to that. How long does it take to really equilibrate? How long do recurrences look like? And if you look at this correlation functions, higher order correlation functions, we can really see if something is local equilibrium or if it just looks like a temperature, if it really has a temperature. And I think if you have these things, the fun starts in playing around with this type of machines. As I said before, this is why it's interesting. You have this normal covariancy, strong coupling. You can look at the quantum noise and entanglement. And that brings me to the end of talk. So basically, the experiment will be done on our atom chip experiment, and basically the two lead students now are Mohamed Tajik and Joao Sabino, who basically work on this quantum thermal machine, and Frederick Möllmer and Frederica Calladino on these excitations and making pump probe experiments and things like this. Of course, there's lots of theory collaboration with it, and there was mostly also Markus Huber, who just joined us at the Atom Institute, Jens Eisert and Yasser Omar for that. And so there are some of the people we come there. These are the two instrumentalists here. These are guys from Lisbon. This is Jens's group and Markus Huber's group. Good. So that I hope I lost my time.
No, perfect.
Perfect.
Questions?
Okay, great. Perfect.
Questions?
Good.
Yes, Gabriele.
Hello, Jörg. Thanks a lot for the nice talk. It's nice to see experiments in quantum thermodynamics. We need many more. One question: do you expect a quantum advantage in your thermal machines, so over classical machines?
Okay. How do you define that? I mean, one thing that we have is we have advantage that we know about our back and about our piston. We know more than you would know in a classical thermodynamic machine. If you get an advantage out of quantum recurrences, and of normal covariancy, then I think we can very clearly see that. We can produce entanglement. If you would see that, looking at anomalous heat flow, not in a trivial way, like with two spins, but really in a macroscopic system, which of tens of thousands of atoms, because of entanglement, I think I would trust that as a quantum advantage. Or
thank you.
But I don't know how do I'm not a quantum thermodynamics person. I'm playing with atoms. I'm just having fun. And so the question is that what would be really one of the things that we had heated discussions about, how do you measure temperature and how do you measure, and what is work? Because people usually say, oh, I take my work meter or I take my temperature meter. And as an experimentalist, I tell them, no, this is completely wrong. The only thing I have is a picture with 10,000 dots. And you tell me how you extract temperature from there. I don't measure temperature. I measure correlation functions. I measure correlators. I measure pictures with every constituent of my system is in there. Yeah. And so I think you have to start to redefining some of these notions that are, very much, murky, because you talk about macroscopic systems and systems in a thermodynamic limit. and go back to the system, go back to go to quantum measurement directly if you ask a question on the system. Yeah. And that's why I said, depending on, how much information you get out to, I think this is what you can do with it. And if you can get more information out there, much more information about the system than you would have in a classical thermodynamic process, then I'm sure that you can get a quantum advantage. But it will come from the quantum measurement in the end, and its analysis.
Thank you. Nicole?
Hi, thanks very much for the talk, Jörg. It's great to hear about what's coming up next in your lab. I was wondering, well, it seems very much worthwhile to do these experiments for the sake of the foundational building of an understanding of the science. I was wondering if you think that any of these quantum thermal many-body machines have the potential to be technologically useful.
Yes, I think. If you have understood what they do, if you look at the talk of Joel, you have these one-dimensional systems that look like Luttinger liquids or Sine-Gordon models or something like that in solids. And if you take a spin chain in a solid, you describe it by quantum field theory, then I think you could transfer these things to some solid state devices. And then you might be able to locally cool a place or do something like that with it. But before that, we have to understand what they really do. In the end, I think if you can transfer them to something like, very long molecules which behave like where you can write the quantum field theory down, or at least in parts a quantum field, or have some emerging property which you can map on this thing, I think then you can do something. But I cannot directly tell you, okay, you have to do that and patent it and make your startup company out of it. This is, I can't tell you yet. Yeah.
So it sounds like you think the use might be transferring these techniques to solid states and find a way to cool those.
Yes, in the end, yes. But as I learned over my growth of experiments to stick with a simple system and try to understand them, because if you just jump 2 steps ahead, you get lost. Yeah, if you really want to understand what's going on. But for the moment, I think it's just trying to ask fundamental questions on this type of thermal machines. But I think it's not crazy to think about that if you really know what is required, that you can transfer it to some solid state device or some macromolecule or whatever that you think about. Yeah.
Okay, thanks for your thoughts.
I hope so.
Any more questions? Okay, so thank you very much, Jörg, for